So as Kian said, I've been travelling for, it's more than 30 hours now. And not much sleep, so I'm kind of messed up. So I'm happy for anyone to interject as I talk. If you've got questions, or if I am talking too fast and you don't understand what I'm saying because of my strange accent, then you're welcome to interject halfway through. So LevelDB, the reason I have an interest in LevelDB with Node is because I've written one of the LevelDB wrappers for Node. So we wrap around the native LevelDB code. We provide a Node interface for it. And I wrote it originally for a couple of reasons. One of them was that just because I wanted to write a native add-on for Node, and I was interested in it, and LevelDB was around at the time and seemed interesting. And another because I found myself in a place where I've been pretty frustrated with existing database technologies. I've been using SQL databases for a long time, and I find myself in a place where I'm calling myself post-SQL because managing and maintaining SQL databases is a nightmare. I hate doing it, and I'd rather have databases that are highly available and are done. I don't need a database to have hundreds of features. I just need a database to store my data and to be available to me when I need it. So LevelDB is an interesting building block, and Node is a great platform for putting together these pieces. So I'm going to start off by talking about what LevelDB is, and then I'm going to move into the Node side of it. So hopefully there'll be stuff in here for everybody, even if you're not programming in Node. So as I said, if you've got any questions, feel free to put your hand up or just yell out. Okay, so LevelDB. It's an open source, dependency-free, embedded key value data store. So it's really just a small embedded data store. Works on keys and values and not much else. It was developed in early 2011 by a guy named Jeff Dean and his colleague Sanjay Gemwat from Google. These guys are research scientists in Google, and they took the ideas of Google's big table and then they rewrote them in this small little embedded database product. It doesn't share any code with big table, but it shares a lot of the ideas of big table in an open source code base. It was initially designed for Chromium. They were using SQLite for a while, and it was slow. So these guys said, well, let's make something that's fast for IndexedDB to work underneath that. So they developed LevelDB, gave it to the Chrome guys, made it open source, and the rest is history. So LevelDB works on arbitrary byte arrays. Both keys and values can be just strings of bytes. They don't have to be, ASCII or anything like that. They're just byte arrays. And this includes keys. It's sorted by keys, and it's lexicographically sorted by default. But you can actually change the sorting if you have a different use for different types of sorting. But most of the time, lexicographical sorting is fine. Its values are optionally compressed with Google's Snappy compression algorithm. And Snappy is a compression algorithm that's designed for speed. It doesn't do a whole lot of compression, but it does it really fast. So by default, everything you put in is passed through Snappy. If it gets compressed about 20% or more, then it'll be stored in the compressed form in your data store. It has the basic operations are just get, put, and delete, and there's also another one called batch. That's really just the basics of LevelDB. That's the important bits. And I think that the winning feature for me is these bidirectional iterators. So you can iterate over keys you can start anywhere in the data store and you can end anywhere, and you can go whichever direction you like. And because it's sorted, this makes it a really powerful feature for for querying. And it does snapshots as well. So snapshots are, point in time. This is the state of the database as it is now, and you can keep a reference to different states. It's based on, the core of it is based on an LSM tree, which is a log structured merge. So LSM is used by a few databases actually, but the core idea of it is, if we ignore the topic for a moment and we look at the log and these table files, these are the two main components of an LSM tree, where you've got incoming writes are put into a log. So any puts or deletes are put straight into this log, and the log is stored actually on disk, and it's also stored in memory. And they call it a mem table, but I'm going to be referring to it as a log because it is actually persistent. Even though it's stored in memory mainly, it's also written to disk. Now and again, the memory is, the log is flushed to these sorted table files, and this is where the sorting comes in. So these table files on disk, they're sorted and they're ordered, and what happens when you read values is that you merge these two. So the log has the latest changes, and the sorted table files has the persistent history.
Table, does it have to do with SQL table?
No. No, ignore the, table, just ignore this, table, I'll explain it in the next slide, I think. But they're files that are sorted, and they have a range of keys, each of these files. So when you read a value, you first go through the log to get to these table files, because the log may contain either a new value or it may contain a delete. So you might have something stored in your table files, but a recent write has deleted that entry. So the reads will merge those two into the current data. And there's also a cache sitting on top for common reads, and that's configurable. You can have quite a large cache if you want to store your working set in memory as well. So it can work really fast. By default, it's only about, I think it's 8 megs of cache, but you can configure that. So these sorted table files, this is a concept from within Google. They use this in Bigtable and a bunch of other places. So SST stands for string sorted table. Each of them in LevelDB is about 2 megabytes each maximum, and you can have a lot of them. So if you've got a lot of data in LevelDB, you can have a lot of these SST files. They're divided into 4K blocks. So each file has got a whole lot of these 4K blocks, and it's 4K because that can be read in one chunk. So when it's looking up a value, it'll read in these 4K blocks at a time to look for your value. The final block in each table file is an index that refers back to the blocks and the starting key in each of the blocks. So when you're looking up a value, it'll find the most appropriate or the most likely SST file. Then it'll read the index of the SST file. It'll use a Bloom filter algorithm to find the most likely location within the file for your entry, and then it'll read those blocks to find it. Another interesting feature is that within blocks you can have shared prefixes. So, and this is prefixes of keys. So if you know how, I guess most people probably have an idea of how video codecs work, how you have keyframes now and again that reset the video block, and then in between keyframes you have changes. That's sort of how LevelDB works with keys within blocks. So you have these shared components of the key. So if your keys contain a common part within each block, then it will only store the common part once, and then the shared bit will be pretty much all that's left over. So what that means is that your keys, you don't have to worry about the length of your keys too much, and it makes namespacing fairly efficient. So if your keys have multiple levels of namespacing, then that'll be compacted down, and it'll only store most the common bit within the blocks. Now the reason it's called LevelDB is interesting and a little bit complex, but I'll try and clear it up. So we've got lots of SST files, but they're not just a flat level of start to finish. They're actually ordered into these different levels. At the top we've got the log. So this is the mem table or the log file. That's just incoming values. It's not particularly interesting, except that it has a maximum by default of 4 megs. So, and you can change that, but as the writes come in, when it reaches the limit, 4 megs, then LevelDB will, in the background, in a background thread, will take those values and then it will merge them into a batch of SST files that it calls level 0. Then the level 0 files, when they reach a maximum of 4 files, then one of the files is taken and merged into level 1, and so on. And each level contains 10 times the size of the previous level. So, as new values come in, they're initially written to this fairly transient set of files that are likely, or have a high probability of changing, because the values you're working on recently, in all probability, are the values that are going to change the most. The values that you put in and leave in are more than likely going to be around for a while. So it uses that to to put old values into a set of files that don't change as much, and the newer values can change a lot. Because when you've got them sorted, if you're adding new values in all the time, then you're going to have to do resorting all the time. So that's where the levels come in. It only has to resort within a level and also within just a range within that level. So from level 1, I think maximum is level 7. Each level is 10 times the size of the previous level. So I've got a picture of that. So you've got your cache and your log at the top, and then each of these levels is 10 times the size of the previous level. When writes come in, they go to the log first, then they move into level 0, and as it expands, if your entries stay, then they'll migrate downwards into the lower levels. Reads have to traverse all of the levels. So if it's found in the cache, that's fine. If it's found in the log, then that's great. But if it's not found in those two, then it starts having to hit each of these levels. So when you've got a large amount of data, there's some efficiency issues with looking them up. So you've got to read at least once per level to find a value, unless you find it in a lower level. But it is an efficient way of storing sorted values and not having to repack everything all the time you add things in. Does that make sense, or am I just gibberish now?
That makes sense. So you're only moving 4 megs in to the next level each time?
Yeah, pretty much. And it only does one, well, it actually 4 megs at the log, but 2 megs each time, because the SST files are 2 megs. So it'll take an SST file, and only one from each level where it's doing compaction. And then it'll take the overlapping files in the next level, put them all in memory, sort them, write a new set of SST files.
And that might push another...
Yeah, it cascades down, yeah. And it picks the SST files in a circular motion through each level. So it'll take one file, just almost at random, take one file, compact it, then it'll take the next file in order and compact it. And that can be happening continually, and it happens in a background thread. So
These numbers, do they play an important role? Are they engraved in stone, or just can change anytime?
The number that...
This 10,
No,
100.
that's pretty much fixed. It's 10 times. So
Yeah.
the rules for level 0 and the log are a little bit messy. But once you get to level 1 is 10 megs big. That's how big it is.
Does it use binary system like 2 to the n?
Sort of, yeah. Yeah, that's right. Yeah, it's not exactly, but yeah.
Okay.
So it's 10 times the previous one, all the way up to level 7. which I think when you get to level 7, you've got a lot of data, and I'm not sure how many people actually get to level 7. But LevelDB is used as the backend for